The issue at hand involves troubleshooting a voltage imbalance in a 120/240 volts three-phase electrical system, specifically in a pole barn with a 208 volts high leg. The primary symptom is that when a 120 volts load is applied to either the A or C phase, the voltage on the loaded phase drops significantly, while the voltage on the other phase increases. The B phase reads 208 volts to neutral. Several potential causes need to be investigated systematically. Firstly, improper neutral connection should be ruled out. It is imperative to ensure that the neutral wire is properly connected at all points, including the service mast, the service panel, and all connected loads. A loose or corroded neutral connection can create a high resistance path, leading to voltage imbalances when current flows. Secondly, an unbalanced load across the phases is a common cause of voltage imbalances in three-phase systems. An even distribution of loads can cause one phase to be more heavily loaded than others, resulting in voltage drops on the heavily loaded phases and voltage increases on the lightly loaded phases. To address this, it is advisable to disconnect all loads initially and then reconnect them one at a time, carefully monitoring the voltage on each phase. This process can help identify specific loads that are contributing to the imbalance. Thirdly, a faulty transformer could be the culprit. If the transformer supplying the pole barn is not functioning correctly, it may produce incorrect voltage readings. This situation necessitates contacting the utility company or a qualified electrician to conduct thorough testing of the transformer. Internal transformer faults can lead to unpredictable voltage behavior. Fourthly, an open ground connection can manifest as voltage imbalances and other electrical issues. The grounding system provides a return path for fault currents and helps to stabilize voltage levels. A compromised ground connection can disrupt this stability and lead to erratic voltage readings. The integrity of the grounding system should be verified by inspecting the grounding rods, grounding conductors, and all associated connections. Fifthly, high impedance in the neutral wire can cause significant voltage drops under load. If the neutral wire has high resistance, it will impede the flow of current, leading to voltage drops when loads are applied. In such cases, replacing the neutral wire with a larger size or upgrading the entire wiring system may be necessary to reduce impedance and improve voltage stability. Now, let's consider the troubleshooting steps in a detailed and methodical way. Step 1 involves meticulously checking all neutral connections. Begin by inspecting the neutral connections at the service mast, where the neutral conductor connects overhead from the utility supply. Ensure that this connection is clean, tight, and free of corrosion. Next, move to the service panel and carefully examine the neutral busbar. Verify that all neutral conductors are securely connected to the busbar and that there are no loose connections. Finally, inspect the neutral connections at each individual load, such as lighting fixtures, receptacles, and appliances. Ensure that the neutral conductors are properly terminated and that there are no signs of damage or deterioration. Tighten any loose connections and replace any damaged wires as needed. Step 2 entails balancing the loads across the phases. This involves strategically distributing the loads connected to the A, B, and C phases to ensure that no single phase is excessively loaded. To achieve this, first, determine the current draw of each load connected to the system. This information can typically be found on the nameplate of the appliance or equipment. Next, calculate the total current draw on each phase by summing the current draws of all loads connected to that phase. Compare the total current draw on each phase and identify any significant imbalances. If one phase is carrying significantly more current than the others, consider redistributing some of the loads to other phases to achieve a more balanced distribution. Avoid overloading any single phase, as this can exacerbate voltage imbalances and potentially damage equipment. Step 3 concerns testing the transformer. Given the potential for a faulty transformer to cause voltage imbalances, it is essential to have the transformer tested by qualified personnel. Contact the utility company or licensed electrician to perform comprehensive testing of the transformer. These tests may include voltage ratio tests, insulation resistance tests, and load tests to assess the transformer's overall performance and identify any internal faults. If the transformer is found to be faulty, it should be replaced with a new or refurbished transformer that meets the required specifications. Step 4 involves inspecting the grounding system. The grounding system plays a crucial role in ensuring electrical safety and stabilizing voltage levels. Therefore, it is essential to thoroughly inspect the grounding system to verify its integrity. Begin by checking the grounding rods, which are typically driven into the earth near the service entrance. Ensure that the grounding rods are securely installed and that there are no signs of corrosion or damage. Next, inspect the grounding conductors, which connect the grounding rods to the service panel and other grounding points. Verify that the grounding conductors are properly sized and that they are securely connected to all grounding points. Ensure that there is a good path for electrical current to return to earth in the event of a fault. Check the resistance of the grounding system using a ground resistance meter to verify that it meets the required standards. Step 5 suggests considering upgrading the wiring system if voltage imbalances persist despite the previous troubleshooting steps. In some cases, the existing wiring system may be inadequate to handle the loads connected to it, leading to voltage drops and imbalances. Upgrading the wiring system can improve neutral capacity, reduce impedance, and enhance overall voltage stability. This may involve replacing undersized conductors with larger ones, installing additional neutral conductors, or upgrading the service panel to accommodate larger loads. Consult with a qualified electrician to assess the existing wiring system and determine the appropriate upgrades to address the voltage imbalances. In addition to these specific steps, there are a few other considerations that may be relevant. Consider the age and condition of the electrical equipment. Over time, the electrical components can deteriorate, leading to performance issues and voltage imbalances. If the equipment is old or in poor condition, it may be necessary to replace it with newer, more reliable equipment. Also, consider the impact of other loads connected to the same electrical system. Large appliances or equipment with high current draw can sometimes cause voltage fluctuations that affect other loads connected to the same system. If possible, try to isolate these loads or connect them to a separate circuit to minimize their impact on other equipment. Furthermore, consider the possibility of harmonic distortion. Harmonic distortion is a phenomenon that can occur in electrical systems due to nonlinear loads such as electronic devices and variable frequency drives. Harmonic currents can cause voltage distortion and imbalances, leading to various electrical problems. If harmonic distortion is suspected, it may be necessary to install harmonic filters to mitigate its effects. To summarize, troubleshooting voltage imbalances in a 120/240 volts three-phase system requires a systematic approach that involves checking neutral connections, balancing loads, testing the transformer, inspecting the grounding system, and considering upgrading the wiring system. By following these steps and addressing any underlying issues, it is possible to restore voltage stability and ensure the safe and reliable operation of the electrical system. Remember that working with electrical systems can be dangerous. If you are not comfortable performing these troubleshooting steps yourself, it is always best to consult with a qualified electrician.